Okay, hi everyone. This is week 9, chapter 9 from Levenspiel. We'll be talking about temperature and pressure effects. Just a few announcements. Homework 6 is due today or within the next couple of days. Please make sure to submit it and make sure to submit all your homeworks before next week. So next week will be a review week. We're going to go over parallel reactions, series reactions, and temperature and pressure effects. You're going to have an exam practice set. And then the week after will be your second exam for the semester. Okay, so submit your homeworks, go over your homeworks, and just be prepared for your exam. Okay. Let me get this laser guy. Let's start the presentation here. So schedule for this week, again, we're going to talk about temperature and pressure effects. Last couple of weeks, we talked about parallel reactions, series reactions, and how, to favor a certain reaction, how to control the concentration of the intermediate in your products and other issues. And now we're going to introduce the idea of having an energy balance as well as a mass balance, right? So if you recall, when we were deriving the performance equations for different types of reactors, we were always assuming that the system is isothermal. We don't have any heat effects. So now we're going to move to the case where the systems are adiabatic, where you do have temperature change within your system. However, it's still a closed system and you don't have a lot of heat exchange with the surroundings. Okay, so if you recall, your performance equation, or for any of the reactors we talked about, depend on your inlet conditions, your CA node, CB node, whatever it is, your outlet conditions, your CA, your conversion, all this stuff, your reactor size, right? V over FA node, or tau over CA node is equal to a certain equation, and your rates of reactions, which is minus RA. Minus RA is usually K, which is your reaction rate constant, multiplied by a certain expression. However, we would always take the value of K at a single temperature, assume it's isothermal, etc. So now we're going to start thinking about the effect of temperature and pressure on your equilibrium composition, your rate of reaction, and the product distribution. So what if I have a big temperature gradient between the start of the PFR and the end of the PFR? What if I have a jump in temperature within a CSTR, or within a batch reactor? How would this affect really your conversions? How would this affect your reactor performance? So we need to define the temperature progression within a reactor or a series of reactors. And the idea of defining this temperature change is we always want to design this reactor to have the minimum reactor performance and the maximum possible yield, right? If we over-design the reactor at the single point with the highest possible temperature, we're gonna just have a huge capital cost because our reactor is over-designed. We just designed a huge vessel to accommodate the highest possible temperature. However, if we take a closer look at the range of temperatures, we could possibly optimize such design and also target our yield effectively. And then we'll talk about some heat exchange systems which you would need to approximate this, and how can you control the temperature within the reactor, etc. Okay, so let's start off just talking about thermodynamics, talking about briefly some simple thermodynamic ideas. So if you recall, you have a position of equilibrium, right? If I have a reversible reaction, A goes to R, and I have a forward and backward rate expressions, or so in your book, this is the expression usually used. AA goes to R plus S. S, right, to usually have a reaction rate constant, small k1. And you need to remember that we also have a second expression here, which is the capital K, which is your thermodynamic equilibrium constant, right? So the capital K, which is your thermodynamic equilibrium constant, and you've taken this in all your chemistry courses, it's the concentration of products, so it's CR to the power R multiplied by CS, or C of S to the power S, concentration of S, divided by the concentration of A to the power A, right? And this is your thermodynamic equilibrium constant, and this is different then your reaction rate constant, right? And you have to remember this. Don't forget these simple things you take from chemistry because, you know, the science does not change. And if it's a reversible reaction, I have K1 and K2, for example, then my thermodynamic rate constant will be the rate of my forward reaction divided by the rate of my backward reaction, right? So it's going to be K1 over K2. And just remember, these are small k's. This is a capital K. So these two parameters are distinctly, they represent similar ideas, but different formations or different formats. And you know, we always have a position of an equilibrium, whether it's a reversible reaction or an irreversible reaction. This position of the equilibrium depends on the temperature, depends on the concentration. So if you recall Le Chatelier's principle, if I have a higher temperature, my reaction will be to the right, lower temperature reaction to the left. If it's exothermic, endothermic, all of these ideas, which you have covered before in 200 in your chemistry courses, etc. And we also have heat effects associated with the reaction. So if you recall, this is sort of your Arrhenius type format where d ln k over dt is equal to delta HR divided by RT squared, where delta HR is the enthalpy of reaction. And if I take this for two expressions, or if I integrate this between K1 and K2, or between T1 and T2, I'm gonna get this expression on the right-hand side, which we have sort of seen a very similar expression previously for the reaction rates. So we've seen ln R2 over R1 is equal to minus EA over R 1 over T2 minus T1. Alternatively, it could be written as ln capital K2 over capital K1 is equal to minus delta HR over R 1 over T2 minus 1 over T1. This is your reaction enthalpy. These are your thermodynamic equilibrium constants. And one thing to note is that your equilibrium composition, which is governed by your equilibrium constant here. So your equilibrium composition is the composition of these three species at equilibrium. It's governed by this equilibrium constant. And as we can see from this equation, this equilibrium constant changes with temperature, right? So if I increase my temperature, K2 value will change. You know, if I move from T2 to T1 or from T1 to T2, the value of K, the capital K, which is the thermodynamic equilibrium constant, changes. And this means that the equilibrium composition changes as well. So just remember these ideas from basic thermodynamics as we progress through this chapter. And also, usually in these types of, or in this level of analysis, or usually in engineering analysis, we assume that the reaction rate is independent of temperature. Of course, if you want to get into real details, you want to really get into the chemistry of it, delta HR changes with temperature. However, it's usually a weak function. And you should also remember that the reaction enthalpy is independent of temperature when, you know, summation of the specific heats of the products minus summation of specific heats of the reactants equals to 0. So basically the CPs of the products and the CPs of the reactants are comparable. Okay, so let's talk now in details about this thermodynamic equilibrium constant. Let's talk about this capital K parameter and how does it change with temperature really. Okay, so let's move on to the next slide. And this slide here, or this chart here, shows the effect of temperature on your equilibrium conversion. So XAE is the equilibrium conversion for two cases. The first case right here is exothermic. And the exothermic case, your K is much less than 1 or is significantly smaller than 1. And your endothermic reaction, or K, is much larger than 1. And these two lines are equilibrium lines. And by equilibrium lines, I mean the rate of forward reaction is equal to the rate of backward reaction. So the overall change in number of moles of A is equal to 0, right? A minus RA equal to 0 does not mean that the reaction is not happening. All it means, so just remember the definition of minus RA. So this is d NA by dt, right? And this means that the number of moles of A does not change with time, right? So if I have a batch reactor, or if I have a CSTR, and I'm introducing a feed, then when we are at equilibrium, when the number of moles of A, the concentration of A here is the equilibrium concentration. Concentration of A does not change, does not mean the reaction is not happening. It just means that if I introduce 50 moles, 25 will react, and I will always have 25 moles left in my reactor, right? So this number of moles does not change. However, I still have a reaction happening throughout this process, okay? Something to really keep an eye on, or to try to understand these concepts now: equilibrium versus non-equilibrium, steady state versus non-steady state. You know, as you progress, or as you get closer to graduating or becoming a senior, you need to start differentiating between these ideas correctly. Okay, so let's look at this chart. One thing we need to notice is that the thermodynamic equilibrium constant is not a function of pressure. It is only a function of temperature, right? The equilibrium constant does not change by the presence of inerts. It's only a function of temperature. And even though like it's not a function of pressure or not a function of inerts, however, they can be used to influence this value of K. So for example, if I have a gas phase reaction and K is the concentration of products over the concentration of reactants, could always play around with the pressure to change this ratio, or you know, have different pressures in different regions of the reactor to change this ratio and control my system. Okay, another thing to note is that when K is much larger than 1, that means that we have an almost complete conversion. So as you can see here, XA is very close to 1. The reaction is considered irreversible, right? So if K is much larger than 1, your conversion is very close to 1. I almost have a complete conversion, and your reaction is practically irreversible, right? It just goes to completion. On the other hand, if K is much lower than 1, it means that the reaction will not proceed. So as the temperature increases, the reaction does not proceed. In fact, conversion drops significantly. And this is possible for exothermic reactions, right? So if I have an exothermic reaction where as the reaction happens, I'm always releasing heat and the temperature is increasing, unless I have a way to effectively remove this heat and keep the temperature low, my conversion is going to drop as the temperature increases. Also, as the temperature increases, the equilibrium conversion increases for endothermic reactions. Conversely, as the temperature increases, the equilibrium conversion decreases for exothermic reactions. And yeah, this is just the general relationship between your thermodynamic equilibrium constant, your conversion, and your temperature. And you need to understand these types of relationships. Okay, so let's have a look at our first example today. So in this example, I'm given a reversible reaction. It's A goes to R, back and forth, right? Completely reversible. And I'm given some thermodynamic information. You can see here, I'm not given any information about CA, CA note, just thermodynamic information. First piece of information is delta G, which is your Gibbs free energy. And again, it's important for you to remember this. You must have seen this before, but delta G is equal to minus RT ln K, where this is capital K, this is your thermodynamic equilibrium constant right here. Okay, so delta G, I'm given a value minus 14,130 joules per mole. I'm given the reaction enthalpy right here, which is at 298 degrees Celsius. So they're both at 298 degrees Celsius. It's minus 75,300 joules per mole. One thing to remember, negative means exothermic, positive is endothermic, okay? So you should always remember this about this number. This is the notation we're using in this course. This is the general notation used everywhere. However, some books like to reverse it. Another thing, we're told that CPA, the heat capacity of A, the products, is equal to the heat capacity of the reactants right here. So therefore, the difference specific heats is equal to 0, right? So there is no difference in specific heats. And what this piece of information tells me, it tells me that delta HR is not a function of T, right? Is not a function of T, right? When the CPs or when the heat capacities of the reactants is equal to the heat capacities of the products, then your reaction enthalpy is not a function of T. And you're being told that, okay, so I have a system and I need a conversion, I need to achieve a conversion of 75% or greater, right? Give me the conditions to achieve this conversion. And by conditions, I mean temperature, right? There is no other thing you can really control in the system. Okay, so if I want the temperature to achieve a high conversion, and in these types of problems, you follow sort of the same approach to solve or to tackle these types of problems. First idea or the first thing you need to get the temperature is you need to get your thermodynamic equilibrium constant, right? I need to get this guy. I need to get this capital K value here. And as you can see, I'm given a value for the Gibbs free energy. I'm given R, given T, 298. So I'm given G at 298. I know T is 298. So I can get K at 298. This is what we're doing here. So the first step, I'm going to use the equation, which is delta G or minus delta G is equal to ln, or delta G is equal to minus RT ln K, sorry. So minus delta G over RT is equal to ln K. You take the exponential, you plug in your numbers, and you get a value for K, which is your thermodynamic equilibrium constant. Okay, so I have a value for K here. So what do I do with that? I need to get a conversion of 75% or higher. And I have one value for K. So now I'm gonna develop or, write an equation of K as a function of temperature. And this is what we do here. So if you recall previously, we said that on the right hand side here, we have an equation where ln K2 over K1 is equal to minus delta HR over R, 1 over T2 minus 1 over T1. And after getting K1 and T1, I'm going to plug it into this equation. So I have an expression where I have K2 and T2, right? So I have ln K2 over 300 is equal to, and 300 here, this is K1, right? Just so that you don't confuse it with the temperature. Right, ln K2 over K1 is equal to delta HR or minus delta HR, which is 75/300 over R, 1 over T2 minus 1 over T1 here. So I have an expression for K. If I rearrange this guy, I can get an expression where K is equal to exponential 9057 over T minus 24.7. And this is an equation of K versus T. So I have an expression for K versus T. So how can I get from this point here to this point here? So how can I get from having an expression for the thermodynamic equilibrium constant to the reaction conversion? So you need to remember the definition of the thermodynamic equilibrium constant, which is K is equal to CR over CA, right? So again, we said your thermodynamic equilibrium constant is the concentration of products over concentration of reactants. You should know this from your chemistry courses or from the basic courses. And I'm going to rewrite these concentrations in terms of conversion, right? So CR is equal to CA naught XAE. And if you recall, we've covered this in case number 6, chapter 3. And CA is equal to CA naught 1 minus XAE, right? So the concentration of A is equal to initial concentration 1 minus equilibrium conversion. And the concentration of the products is the initial concentration of the reactants multiplied by the initial conversion. And this is equal to XAE over 1 minus XAE. K is equal to this. If I rearrange it, I can get an expression for XAE in terms of K right here. Okay, so now I have two things. I have an expression for K in terms of as a function of temperature, and I have an expression for XAE as a function of K. So using these two equations, I can develop a relationship between temperature and conversion, right? And once we get this, once we tabulate this or plot these values, I can determine the temperatures that will help me achieve conversion of 75% or greater. Okay, so let's do this. So this table here just shows your temperatures, right? Degree Celsius, degree Kelvin. I'm plotting the K values using the equation we just derived. K is equal to exponential, 75300 over R, it was 9057, minus 24.7. Plug in my temperature, get my K, so I have all my K values at different temperatures, and this is Kelvin, right? Just be careful. And then from the other equation, I can get XAE. So now I have XAE as a function of temperature. And if I take a look here, in order to achieve, so we're looking for what? We're looking for conversion of 75% or greater, right? So this prompt here, I need a conversion of 75% or greater. If I look at my conversions here, this means that this is really the boundary, and this is the area where I want to operate, right? I want to operate at conversions of 79 or 75% or higher, greater than 0.75 basically. And this corresponds to a temperature of 348 and lower, right? So 348, 338, or in Celsius, 75 Celsius, 65, etc. And ideally you don't want to operate below standard operating conditions. You don't want to operate below 25 Celsius, especially if the conversion is already high at 25 Celsius. You don't want to introduce cooling elements into your reactor needlessly, right? So I'm gonna fix my temperature range between 75 Celsius to 35 Celsius, and this will be the temperature range where I want to operate. And this temperature range, I meet the criteria of having a conversion greater than 75%. Okay, so after you tab, let's look at this table in graphical format. And as you can see here, this is the equilibrium conversion on the y-axis, your temperature on the x-axis. And if I plot these points, I get this nice equilibrium curve. And this is called the equilibrium conversion curve, which we will get to, or we will refer to throughout this chapter. And in order to achieve a conversion of 75%, I just read the value of my chart, and this corresponds to temperature of 78 degrees Celsius, right? And any temperature lower than 78, my conversion increases, right, along this line. Any temperature higher than 78, my conversion decreases. So now let's look at a bunch of parameters here. Let me erase this guy. Let's look at a bunch of different things. So for a conversion of 75% or more, T must be less than 78 Celsius, as we just said. This line right here, the solid black line, is the equilibrium data, or equilibrium line at reaction rate equals to 0. You have low rate as the equilibrium is approached, and if you think about my conversion here, my reaction rate is very high at the bottom of this chart, and as I get closer to equilibrium, my rate approaches 0, right? Because on this line, the reaction rate is 0, so the further I get away from the line, the higher my reaction rate will be. This is what this red arrow represents. So the rate of reaction is high at the farthest point away from the line, and then the rate of reaction drops to 0 as I get closer to the equilibrium line. Okay, and this red arrow here represents your isothermal reaction path, right? And along this isothermal reaction path, your reaction rate starts very high, and then it starts dropping as you get closer, or as you move closer to equilibrium. Okay, so now let's introduce 3 new charts, and these charts are the temperature, composition, and reaction rates as a function of each other and as a function of temperature. So on the left-hand side here, I have a chart showing the composition versus temperature. Composition on the y-axis, temperature on the x-axis, and I have 3 locuses or 3 lines for the 3 different reaction rates. In the middle here, I have a reaction rate versus temperature. On the y-axis, I have my reaction rate. X-axis, I have my temperature, and I have 3 lines of constant concentrations. And on the right-hand side here, I have my reaction rate on the y-axis, my composition on the x-axis, and I have 3 lines of constant temperature. And you need to remember that for a single homogeneous reaction, concentration, reaction rate, temperature are all related. It's not a linear relationship. It's not a quadratic relationship. It's a very unique type of relationship. It depends on your equilibrium concentration, your equilibrium constant, your concentrations, the position of equilibrium, the initial compositions, the temperature you want to operate. Are you operating isothermally, non-isothermally? All of these factors now start playing a role in your system. However, realistically, the first plot on the left-hand side here is the easiest one or the most convenient one to use. And this will be the one we will be using throughout this chapter. And since it's concentration, usually we write this concentration as a conversion because it's easier to translate conversion, or it's easier to relate conversion to your targets or to your metrics in terms of operating the reactor. Okay, so let's have a look here at three main systems. The first system on the left-hand side here is, or the general shapes basically for the temperature conversion plots for the different reaction types. On the left-hand side here, I have conversion versus temperature for an irreversible reaction. And as you can see, this is the general rate, this general shape it takes as my reaction rate increases. My locus of equilibrium conversion changes. For a reversible exothermic, this is what the plot looks like. I have my equilibrium line where R equals 0, and my reaction rates are sort of curved to meet this equilibrium line. And for a reversible endothermic reaction, my equilibrium line looks sort of the complete opposite for the reversible exothermic, and my reaction rate lines also curve to meet this line at that certain point. Okay, so just be aware of these different shapes. So you might see this if you become a reactor technologist or something. You might end up seeing these types of plots for your reactor or for your system. Okay, and up to now, we've always only looked at isothermal reaction pathways. So up to now, we always had a single temperature point, just one temperature. We have one reaction rate at this single temperature, and we have one conversion, right? This is how we always operated, or this is how we always solve these types of problems. However, now if we want to look at our changing temperature in our system, want to look at the effect of having a changing temperature both with time or with space, we need to take a closer look at these types of charts. And in order to reliably use these charts, we need to have good kinetic data, right? So we need to have good experimental data on how the reactor operates, how the catalyst operates, how the reaction proceeds, etc., so that we can construct this sort of table with some confidence and use it to predict the reactor performance. Okay, so how do we use these charts to determine the size of the reactor required for a given duty and a given temperature progression, right? So if I give you a reaction, I tell you, okay, I have this reaction, I have this amount of heat duty from this reaction, and I want to operate this reaction over this type of temperature progression. So I have a feed which is at 25, and I want my product to be at 70 Celsius, and my reaction rate releases 50,000 kilojoules per moles of energy. You're just given some thermodynamic data, and you're being told, determine the best reactor size. This is the approach to do it. So from a defined feed point, you're given CA node, CB node, etc. I'm going to draw my reaction path on the XA versus T plot. And this is called the operating line. And the idea of operating line, again, I'm sure you've seen it in mass transfer. It's a very popular idea, or it was a very popular idea when developing all of these equations analytically and by hand. And it's good to try and get an understanding on how these operating lines work, how to construct them, etc. However, nowadays you can always use Aspen, you can always use GPrism, we have GPROM, sorry, you have all of these software which will do all of these calculations for you automatically. But having a basic understanding will help you not use these tools as a black box and just not being aware of how to troubleshoot strange results, or not being able to catch out wonky numbers and things like that. So anyways, the approach, I'm going to draw the reaction path on the XA versus T plot, which is my operating line. I'm going to read the rates along this operating line and then tabulate XA versus minus RA. Then I'm going to plot 1 over minus RA versus XA. And then I'm going to use, similar to the ideas we've discussed previously, I'm going to either integrate the area under the chart for a PFR or take a box under the chart for a CSTR to get the value of V over FA naught, which is my reactor volume. Okay, so generally, just having a quick look at 3 cases. First case on the top here is for a PFR with an arbitrary temperature profile, just a random temperature profile, a thought experiment if you want. I have XA versus T. I start at temperature 1. My temperature decreases, and then it increases, and then it decreases again. And this is my operating line for the system. From this operating line, I'm going to read the reaction rates from these curved lines here in the middle. So at T1, I'm going to read the reaction rate 0.05. At this point, I'm going to read the reaction rate maybe 0.01 here. T2 reaction rate 0.02. T3 reaction rate 0.01, go back to 0.02, all of this stuff. And then I'm going to plot minus 1 over RA versus XA, and I'm going to get this sort of curve. If I integrate this curve, I'll get the area under this curve. This will be the volume of the, or V over FA naught for the PFR for the system. Now let's look at a second type of system where I have a PFR with 50% recycle and a rising temperature profile. So along this PFR, I have a temperature increase from point C to point D, right? Temperature just increases along the reactor. Same thing, I'm gonna read my, at every temperature point, I'm gonna read both the conversion and the reaction rate, right? So this temperature, my reaction rate 0.02, conversion 0.4. If I move up to this point, my temperature is T2, reaction rate is maybe 0.01, and my, or 0.03, and my temp, or my conversion is 0.5. Get to this point, I have T3, my reaction rate is 0.05, conversion 0.6. I get all these points, I plot minus 1 over RA versus XA. I have an area under the curve, and I integrate this area to get the volume of the PFR, right? And again, here I have 2 boxes because, you know, I'm comparing, you know, the example in your book is trying to compare a CSTR to a PFR, and always remember for a PFR, I'm integrating the area under the curve, whereas for a CSTR, I'm just taking a box corresponding to the last, just taking a box corresponding to the last CA naught, XA naught minus RA, or CA, sorry, XA minus RA at the output, and I just take a box here and I get the volume of the reactor. And this is what we see at the bottom plot here. So the bottom figures for a CSTR, I have a single operating point. So I have a CSTR and I'm only operating the CSTR at a single point of 1 temperature, 1 conversion, 1 reaction rate. Okay, I take, or I have a temperature and I have a conversion. I read my reaction rate off this chart. I plot minus 1 over RA versus XA, and I just determine the area of this rectangle here, and this will be the volume over FA naught for the CSTR. And this is the general idea, this is the general approach to calculate your reactor volume from these types of figures. Okay, so now let's have a look at 3 main ideas right here. So the first one, so I have three plots, sorry, again, XA versus T. On the left-hand side, I have a plot for the irreversible reaction. In the middle, I have a plot for reversible endothermic, and on the right, I have a plot for a reversible exothermic reaction. And I want to determine the minimum reactor size, right? So in order to determine the minimum reactor size, I need to determine the highest possible reaction rate, right? And you always need to remember that the reaction rate will always increase with temperature at any composition. So your highest reaction rate will occur at the highest allowable temperature. Okay, so let's look at the left-hand side here. Again, your reaction rate always increases with temperature, and your highest reaction rate will be available at the highest maximum allowable temperature. So I need to determine the maximum temperature which I am allowed to operate. And this point, or this line here, will be the line of highest reaction rates, and the highest reaction rates will give me the lowest or the minimum reactor size required to achieve the conversion you want. Okay, so now for an endothermic reaction, so we're looking at the figure in the middle here. A rise in temperature will increase both the equilibrium conversion and the rate of reaction. So increasing the temperature, if I take a look here, will increase both the equilibrium conversion, which is this line right here, and my rate of reaction, which are these lines right here. So similar to the previous point, so similar to the figure on the left-hand side here, I want to always operate at my maximum allowable temperature. And because at the maximum allowable temperature, I'll have the maximum possible reaction rate, have the maximum possible conversion, and therefore I'll have the, it will allow me to effectively design my reactor. So let's just revisit these two. So for an irreversible reaction and for a reversible endothermic reaction, you want to operate at the highest possible temperature you can operate at. And this highest possible temperature doesn't mean, you know, how high you can turn up your furnace. It means how high your materials of your reactor can support, you know, what's the thermodynamic data for your species available, what's the production metric you're targeting. So if I want my products to be at 95 Celsius, then maybe I want to operate at this highest possible temperature. If I can only remove heat at a certain rate, I want to operate at this highest possible temperature, etc. And these two cases are opposite to the case on the right here, which is a reversible exothermic. And this is really the unique case in this type of situation. So for a reversible exothermic reaction, as the temperature increases, I have two opposing factors in play here, right? The first factor is the rate of forward reaction increases. However, the conversion will decrease. Okay, so as temperature increases here, so if you think, so this solid black line is my equilibrium conversion, and these curves are my reaction rate curves. And as my, so I have two opposing factors when I have a reversible exothermic reaction. First one, as my temperature increases, my conversion will decrease. So you can see the solid black line decreases as temperature increases, right? Second factor is, as temperature increases, my reaction rates, which are these curves here, increase, right? So as my temperature increases, my reaction rates increase. They always have a maximum and then they decrease again. However, they will increase initially. Whereas for the conversion will always decrease with increasing temperature. So how do I operate this system? I operate this system, we always start at the highest possible temperature. So I start at the highest possible temperature, and then I cool my system so that I remain at the locus of maximum reaction rates, okay? So again, for a reversible exothermic system, I want to start operating my reactor at the highest possible temperature, and then I cool my reactor with time or with length if you have a PFR, so that I maintain the temperature along this locus of maximum reaction rates. And this way I can maximize my reaction rate and increase my conversion along as the reaction progresses or as the reactor continues to operate. Okay, so this is really the unique case here. The two left-hand side cases, my reversible reaction, my reversible endothermic reaction, I just need to operate on my maximum allowable temperature, because my maximum allowable temperature, I'll have my maximum possible conversion and my maximum possible reaction rate. Whereas for a reversible exothermic reaction, my conversion will decrease with increasing temperature, and my reaction rates will increase up to a maximum. So I want to operate initially at my maximum possible temperature and then decrease my temperature as my reactor continues to operate, or along the length of the reactor, depending whether it's a PFR or a CSTR. And this way I can control the reaction rate and increase the conversion. So I'll control the reaction rate by slowly decreasing my temperature to maintain or to keep or to stay on this operating line of the maximum reaction rates, or, you know, as you can see the blue arrow here. And if I control this effectively, I'll always be operating at the maximum possible reaction rates, and I'll also achieve a higher conversion, right? You don't want to operate this just at the maximum possible temperature, because you'll operate at a suboptimal conversion and a suboptimal reaction rate, right? I want to control it to stay on this maximum line. Okay, so let's have a look at an example here. This is example 9.2 from your book, page 213. And in this example, I have A going to R and R going to A, forward and backward reaction. Initially, I don't have any R. I have experiments, and you're given some information. So you're being told experiments in a batch reactor show that at 65%, 58% of A is converted at 1 minute, and at 25% and at 25 Celsius, 60% of A is converted at 10 minutes. You're being told assume it's reversible first order kinetics and build a conversion versus temperature chart. Okay, so I'm given some information. I'm given temperature, conversion time, 65, 58, 1, and then 25, 60, 10. Given two pieces of information. You're being told it's a reversible first order kinetics, and you need to prepare basically an XA versus T plot similar to what you've seen before. So for this type of problem, first thing we need to get is a relationship between conversion and temperature rate, or conversion and reaction rate constant, just conversion and a temperature dependent parameter. So if you recall from chapter 3, I think it was week 2, A going forward to R, going back to A, this is case number 6 for a first order irreversible reaction. And this is sort of the representative equation for this case. K1 over T divided by XA equilibrium is equal to minus ln 1 minus XA over XA equilibrium. So if this is the first time you see this, go read the slides from chapter 3 in week number 2. So anyways, I have this equation, K1T over XA equilibrium is equal to minus ln 1 minus XA over XA equilibrium. I'm given some data. So from the batch run at 65 Celsius, so I'm told at 65 Celsius, my equilibrium is 58.1. And this is not the equilibrium conversion, this is the actual conversion, right? So I have two conversions here, my actual conversion and my equilibrium conversion. My equilibrium conversion occurs when the reaction rate is 0. Your actual conversion occurs when your reaction rate is not equal to 0, right? So this system is not at equilibrium, right, at this point. So anyways, and this is the same system we've talked about previously, and this is actually example 9.3 from your book. But previously we've shown that, or we've calculated, and then the previous example on these slides, we had a table of this table right here where we're able to calculate XAE versus temperature, right? So at 65 Celsius, XAE is 0.892. Let's go back to the example. So at 65 Celsius, XA equilibrium is 0.892. I'm going to plug my values into this equation right here. I have K1 multiplied by 1, XAE at 65 Celsius is 0.892. So I plug this value here, XAE. And instead of time, I'm going to put 1 minute. Instead of XA, I'm going to put 0.581, which is the conversion I have at 65 Celsius. And from this equation, I can get my equilibrium constant, right? So in this case, K1 is 0.942 at 65 Celsius. So I can get a K1 at 65 Celsius. I can repeat the same process for second piece of information here at 25 Celsius, 60% conversion of A at 10 minutes. So I can repeat the same process. I just get the equilibrium conversion of A at 25 Celsius, plug it here. This value becomes 10, this value becomes 0.6, and I can get K2 at 25 Celsius. And if I do this, I can get at 25 Celsius, I have my equilibrium constant to be 0.0909. Okay, so I have two K values at two different temperatures. From these two K values at two different temperatures, if I get the ratio, I can now solve for my activation energy, right? So here K1 338, K1 at 298, I have my values is equal to your pre-exponential constant, which is the same. So these two guys will cancel out, and then I have exponential minus E1 over RT, 1 divided by minus E1 over RT2. If I solve for the activation energy here, I can get the value for the activation energy to be 48900. And basically I have a full definition for K1 over temperature. So I have K1 is equal to now 3/4 times 10 to the 6 exponential my activation energy over RT. So I have an equation of K1 versus temperature. Okay, so what do we want to calculate? So let's just remember, what do we want to do? Oh, okay, so we want to get a reversible, so no, we want to get the conversion versus temperature chart. Okay, so I want to get an XA versus temperature chart. And so far I have my K versus T. So how do I get from K to X? Again, similar to example 2, I'm going to use the two equations we developed, right? The first equation was the thermodynamic equilibrium constant as a function of temperature. And the second one is the relationship between the conversion and the thermodynamic equilibrium constant. So how do we jump from your reaction rate constant to your thermodynamic equilibrium constant? Just recall the definition. So your thermodynamic equilibrium constant is K2 over K1, which is the reaction rate constant for the backward reaction, divided by the reaction rate constant for the forward reaction. Okay, so I have K is equal to K2 over K1. So I can get K2 at 338 at 298. So I can get a value for K2 as well. And similarly, I can get the activation energy of K2, right? So now I have a full picture of K2 over K1. Okay. So after getting K2 over K1, I have a relationship for X as well. So I can now start preparing a chart similar to the previous charts we looked at, which has conversion versus temperature. And if you plot all these values, you're going to get conversion on the y-axis, temperature on the x-axis, and you're going to get this chart. If you're having a hard time seeing how we got this chart, read the example in your book, think about it, spend some time to think about it. It's not obvious. If you're still struggling, come to office hours. We'll plot it out together. Okay. So again, along this chart, and remember, in this case, I have it's a reversible reaction, right? And if we recall previously, for reversible exothermic, I need to operate along the locus of maximum reaction rates. And this is an exothermic reaction because we said previously that, we mentioned that previously. So here, if I look at this chart, which has conversion versus temperature, and I draw my maximum allowable temperature here of 95 Celsius. So if my system is irreversible, or, my system is irreversible or reversible endothermic, I will operate at the maximum allowable temperature right here, where I basically determine my reaction rate, and then this will be my operating point, and I want to always operate at the maximum allowable temperature. However, if my system is reversible exothermic, I need to draw a line along the maximum reaction rates, right? This will be the locus of maximum reaction rates. And as you can see, these curves, so there are two things to note on this chart. The very first top line here, which is the big curve extending from 1 all the way to here, and you see it's pointed by equilibrium. This is actually your equilibrium conversion. So this line right here, this is actually XA versus T. And at equilibrium, so basically at or equals 0, XA versus T represents the very top curve here. And then all of these smaller curves represent your reaction rates, or represent your conversion versus time at different reaction rates, right? So if my reaction rate is 0.05, my conversion versus time will look like this. If my reaction rate is 1, my conversion versus temperature will look like this, etc. Yeah, so these lines are conversion versus temperature at different reaction rates. At the very top is conversion versus temperature at equilibrium, or at a reaction rate equal to 0. Okay, so I'm gonna draw a line just joining all the maximum of all these curves, so all the maximum point of all these curves. just join them with a line, and this will be the locus of maximum reaction rates. And this will be the line where I want to operate. This is the optimum operating line for temperature progression for the case where I have a reversible exothermic reaction. So if this reaction is reversible exothermic, I want to operate, start at my maximum allowable temperature here, and then decrease my temperature backwards so that I stay on this locus of maximum reaction rates. This way I always have the maximum possible reaction rate, and I'm always getting the highest possible conversion for any reaction rate, and eventually, once I reach equilibrium, I would have the maximum possible conversion. Okay, so if we take a look at possible, how do we achieve this? How do we decrease or how do we control the temperature along this reactor? Let's introduce the idea of adiabatic operation, okay? And adiabatic operation basically means that there is no heat being transferred between the system and the surroundings. However, there is a change of temperature within the system. Okay, this is the basic idea of an adiabatic system. And for a CSTR here, this is a basic schematic. So I have XA note. Initially, there is zero conversion. I enter at T1. My reaction happens in the system, and then I exit at a conversion of XA and a temperature of T2. Whereas on the right-hand side here, I have a PFR. And again, for a PFR CA note, initial concentration is zero, initial conversion is zero. I enter at temperature of T1 and I exit at temperature of T2. And these two cases represent adiabatic operations with large enough heat to cause a rise in temperature or a drop in temperature in your reacting fluid. So if your reaction is exothermic or highly exothermic, you'll see a big temperature difference between the inlet and the outlet of the reactor. And if your reaction is highly exothermic, you'll see a big temperature drop between the inlet and the exit of the reactor. Let's define some parameters here. Cp prime is the specific heat of the unreacted feed. Cp double prime is the specific heat of the completely converted product. So, pure reactants, pure products. Delta HR1 is the heat of reaction per mole of entering A. And if we do an energy balance around the system, and again, you can verify this yourselves if you do a heat balance. So minus delta HR multiplied by XA is equal to Cp double prime, heat capacity of the products multiplied by T2 minus T1 XA, plus heat capacity of the reactants T2 minus T1 into 1 minus XA. This is my basic heat balance. Highly recommend that you try to derive this by yourselves. Make sure you're comfortable with this. If you're having a hard time, come see me on office hours. If I distribute this expression here, I just do some algebra, some rearranging, so I get an expression as a function of XA. And on the right-hand side here, I have Cp prime T2 minus T1. So now I can take out XA and get an expression of XA conversion as a function of temperature change along my reactor and as a function of my reaction rate. Okay, and this expression or this equation is very important. You'll probably see it on your test in some way or form, even though you don't have any problems about it this homework set. However, you're going to get problems next homework set about it. And just a couple of things again. Cp prime is the specific heat of unreacted feed. Cp double prime is the specific heat of the completely converted product. And when XA equals 1, so if XA equals 1, I can rearrange this to get minus delta HR2 is equal to Cp prime delta T, or the delta T adiabatic temperature is equal to minus delta HR2 over Cp prime. So when I have complete conversion, or in the theoretical case of having a complete conversion, XA equals 1, this new parameter is introduced, which is called the adiabatic temperature rise. And to calculate the maximum possible adiabatic temperature rise, you just divide minus delta HR2 by Cp prime. Okay? So again, two equations. First one is conversion as a function of heat capacities, temperatures, and reaction enthalpies. Second equation here, determine the maximum possible adiabatic temperature rise inside the reactor and this is the function of the heat capacities of the feed divided by the reaction rate. Good. So now let's move on. Let's have a look at the plots of this equation. You know, if I plot this equation, what do I see? So on this chart here, I see you have a plot of XA on the y-axis, T on the x-axis, and I have a bunch of lines here. I'm mainly concerned about, or I'm mainly interested in these three lines. First line in the center here, it's a straight line. I have isothermal conditions, and under isothermal conditions, temperature or the conversion is independent of temperature, right? Temperature does not change, it's just one vertical line. Okay, second line here on the left-hand side is endothermic reaction, which means my reaction rate enthalpy is greater than 0. And as you can see, it has a it's curved to the left basically, or you know, this curve moves to the left-hand side. So what's the slope here? So this is this actually has a negative slope, right? So for an endothermic reaction, your plot of XA versus T has a negative slope, whereas for an exothermic reaction, your plot of XA versus T has a positive slope. Let's see if this makes sense. If we take a look at this, this equation right here. So for an endothermic reaction, we said, so for an endothermic reaction, my T2 will be smaller than T1, right? So my reaction enthalpy is positive. So XA versus T is actually positive, right? Or is actually negative, right? The slope of this line will be negative because I have this negative sign here. Whereas for an exothermic reaction, this negative sign cancels with the enthalpy, so the slope is positive. Okay, and this is what this represents. Something to keep an eye out or to think about. And the other thing represented on this chart is as I increase my inerts, whether it's an endothermic or exothermic reaction, my performance of the system approaches the isothermal performance, right? So because once I have inerts, they sort of dilute the heat capacity, or they increase the heat capacity, have more material for this heat to dissipate in, so your system, the change in temperature decreases, right? So for example, if I have a gas phase reaction, I purge it with nitrogen, so the nitrogen will actually eat up a lot of this heat, and this will prevent having a huge temperature increase in the system. Or if you're operating a system, you know, for example, the most common one is a Fischer-Tropsch reaction. I have CO and hydrogen, highly exothermic, so I run it in a reactor full of wax, and this wax eats up all this heat, so I don't have a high or a large temperature jump throughout my reactor. Okay, anyways, so again, I have your adiabatic exothermic, which is the line on the right-hand side. The slope is equal to this, and the slope is constant of if delta HR is constant. On the other hand, you have adiabatic endothermic, which is the line on the left, and the slope is constant if delta HR is constant. Just be aware of these relationships of how these figures look, etc. Okay, let's move on to a few ideas before we end this lecture. So here we have how to determine the reactor size for adiabatic operations of plug flow and mixed flow reactors. And as you can see here, the size of the reactor needed for any given duty. And just take a look at these three charts. I have XA versus T. The top here is the endothermic PFR. I have XA versus T for an exothermic PFR. And then I have at the bottom XA versus T for an exothermic CSTR. And this, in order to determine the size of the reactor, which is V over FA naught, which is the objective of this slide, for the plug flow reactor, I'm going to tabulate the rate for various XA along the adiabatic operating line. Very similar idea to what we talked about before. You draw your operating line from your initial temperature to your final temperature along this or on this XA versus T plot, right? So in this case, I'm drawing the operating line, and then I'm preparing a -1 over RA versus XA plot, and I'm integrating along the path of this operating line to get my reactor volume. Okay. Similarly here, so I have an adiabatic, or is an exothermic PFR, and my operating line is C to D. So I'll run my reactor initially at this temperature and this reaction rate, and I want my products to exit at this temperature and at this reaction rate. I draw my operating line, I read all of my reaction rates versus conversion, I plot -1/RA versus XA, and I integrate the area under this curve to get the volume of the reactor. Whereas for a CSTR, I just look at my final point, right? Or, your final point is we usually approximate the final point where the exit to be equal to what's happening inside the reactor. So, you just find the point of what's happening inside the reactor, the conditions, the equilibrium conditions. You just plot them. I mean, you actually don't need to plot them because it's just a square, but anyways, you can plot them on a -1/RA versus XA and just calculate the area of this, not square, rectangle to get the volume of your reactor. Okay, these are just a general idea on how to deal with these systems, or what's the general approach to design the system. Again, hopefully we can get to the Aspen tutorial covering reactors. Once we get to that point, we could really, or actually Aspen can do a lot of these calculations for you. Maybe not to calculate the volume of the reactor, but definitely to get the relationship between conversion, reaction rate, and temperature. Okay, now let's have a look at a few ideas again towards as we approach the end of this lecture. So here we have these two charts show the best location for the adiabatic operating line. And one thing to remember, that the best adiabatic operation for whether it's a plug flow reactor or a CSTR, we need to look again at the conversion versus temperature line, right? So on the left-hand side here, I have the operations for a plug flow reactor. And if I take a look at the best operating temperature, it's usually an iterative process for a PFR, right? So for a PFR, because usually in a PFR it's hard or it's difficult to control the operation along the locus. So you want to keep your temperature somewhere between your locus of maximums and your equilibrium, right? And with some iteration, some trial and error, you can eventually find this line or find this point of best operation to operate adiabatically. Whereas for a PFR, as we said previously, the PFR, you just find your minimum point or find the point of operation within the reactor, and you just get it on your chart. And the main difference here is due to the performance equation. If we recall, the -1/RA versus XA for a PFR. So if the chart is, or the curve is like this, I only need this final point here, and then I'm gonna get my area by just drawing the square, and this will be the area of the reactor. Whereas for a PFR, I really need to get a locus, or I need to get an operating line, because this operating line, so if this is my operating line, I need to integrate really under the area under this curve. So I need to integrate, or do some hand integration if you want. Basically divide it up into small pieces, calculate the area of your Simpson's rule, all these fancy stuff, if you remember. You integrate there under the curve and you get the volume of the reactor, right? So here is a bit of trial and error to find the best line of operation. Here I just find the point, get the area under the curve. Okay, and I highly recommend you read this from your book. It's page 2 to 3. It has a lot of good information, or a lot of things to think about. You might get a few questions on multiple choice. However, these concepts are slightly more complex, and eventually they're going to click once you work in this field for a while. But as the first time being introduced to them, they're hard to wrap your head around. But anyways, just try your best, read page 2 to 3, and try to get an understanding. So I'm going to talk a bit more about some of these complex concepts for you to get an idea about it. So here again, we're talking about for exothermic reactions, and we're having a look at comparing the operating line for a very exothermic. So I have a very large increase in adiabatic temperature whereas a less exothermic reaction where the increase in adiabatic temperature is much smaller. And from this line, what we're trying to show, or the point Levenspiel is trying to illustrate, is that if you have a very large exotherm or a very exothermic reaction, you want to operate using either a CSTR or a PFR with recycle, okay? Because when you operate with a CSTR or a PFR with recycle, you can really minimize your reactor volume, whereas having a good control over this large temperature increase. You can always use strategies like purging, diluting, you know, all this fancy stuff. But this, you know, think about it, try to make the relations logically. But the general idea, highly exothermic, use a CSTR or a PFR. A less exothermic reaction, you just use a PFR because, you know, you can do the reaction in a much smaller volume. And again, if you relate this to the idea of mixing we talked about before, highly exothermic reactions, you want to have a lot more mixing than less exothermic reactions. That's why I'm operating with a CSTR or a PFR, right? Or a PFR with recycle. So PFR with recycle, as you said, as the recycle approaches infinity, the performance approaches a CSTR because I have a lot more mixing. CSTR inherently has significantly more mixing than a PFR, and better mixing implies better heat transfer, which implies better temperature control, implies you can control you can move your temperature along those locus of maximum reaction rates, as we said previously, and have a better control on how to achieve this. Okay. So again, if we take a look at what does this chart show? Let me remember here. Oh, okay. So this chart shows the effect of having a heat exchange with the surrounding on the operating line, right? So we have this line on the left here. If we recall, this line was for, this is on the line on the left, it was for adiabatic exothermic reactions, right? And I have two lines. The line on the left here, I have a heat removal proportional to T2 minus T1. So if I have a cooling system on this exothermic reactor and it removes enough heat proportional to a temperature drop from T2 to T1, then I can really move my line closer to the isothermal operating line. If you recall, the isothermal operating line is just a straight line upwards. And if I have a good cooling system which can remove the heat, I can operate more isothermally. Alternatively, if I, for some reason, pump heat into an isothermic system, I'll just move away from my isothermal operation and my conversion is actually going to drop, right? And again, for exothermic reactions, you want to operate as close as possible to isothermal conditions, because even though this idea of moving along the locus of maximum reaction rates, it's technically valid, and you want to do this for if you have a reactant which is very very expensive, reactant which is very dangerous, and you want to get rid of it and react it efficiently and quickly, while minimizing recycle, minimizing all of this, then yeah, you want to play with the temperatures to keep the reaction rate at the maximum possible rate. However, if you have an oil and gas, for example, where these types of scenarios are not very common, we operate isothermally so that we have the maximum possible conversion by either cooling. So for example, if you have a reaction, you know, water gas shift, steam methane reforming, all of these reactions, you try to operate isothermally by either removing heat or adding heat. This way, you don't really need to worry about variability, and allows you to have better control of your product, especially if you have a large plant. Okay, so let's have a look at the different cooling methods, right? So now we talked about, or different heat addition and removal methods, cooling and heating methods. So after introducing this idea of, you know, operating isothermally and how to shift this line for adiabatic operations, let's have a look at the first way you can cool this system. So the first method here is, as you can see, I have my PFR. You know, I have a hot feed entering the PFR and cooled product leaving the PFR. And then I have a cooling coil surrounding this PFR. And in this cooling coil, I'm introducing the cold feed at this point, and then the cold feed is going to eat up the heat from the reaction and heat up the feed before it enters the reactor, right? And this system is called a heat exchange with incoming fluid, right? And this allows me, or if I control the flow rate effectively enough, this allows me to have a temperature gradient along the reactor length, right? Because this feed is entering at a high temperature, it's being cooled, or it's entering at a high temperature. I'm having an exothermic reaction here, but this exothermic reaction is being cooled by the fresh cooled feed being incoming in this cooling coil, and eventually my products are cooled. So my temperature along, or actually the chart is here, the temperature along the length of the reactor is dropping, okay? So reaction and cooling, this is the temperature along the reactor. It's dropping between B and C, and then my feed, which is entering this cooling coil, is being heated between A and B, okay? And this is type of system will actually help, or if controlling it is obviously complex, right? Because I need to play with my reaction rate, the length of this coil, all of these different parameters, and depending on the nature of the fluid, etc. However, in an ideal case, this is a good scenario where you can really control your operating temperature along the locus of these maximum reaction rates. Okay, let's move on. Second scenario here. Second scenario, I have a hot feed, and I have 3 small reactors, or maybe different parts of the reactor, etc. First reactor is operated at high temperature, second reactor operated at an intermediate temperature, and the third reactor is operated at a cool temperature, right? So I put my reactors in series. I just divide the reactor into 3 smaller reactors, or get my optimum volume, divide it over 3, and run 3 smaller reactors. And I have interstage cooling, right? And this scenario is called multi-stage operation with interstage cooling, right? So I'm operating 3 reactors at 3 different temperatures. I have cooling between them, and this is fairly common actually, especially when you have gas phase reactions. A lot of the time you want to do this to minimize, or for safety issues, and for other issues, if you have safety, if you have a toxic gas, or if you have a highly explosive gas, you want to operate using multi-stage system. This allows you to purge at any point. You never have a huge volume of gas at an extremely high temperature at any point, etc. And you can always purge intermediately. You can always, have recycles intermediately. Gives you better control. Anyways, you need this system when it's difficult to introduce the required heat exchange within the reactor. That's why we use it a lot with gas phase systems, because the heat capacity of gases are much lower. So because the heat capacity of gases are much lower, if I have a huge volume of reactor, it will make it very hard to really cool down the entire reactor effectively. Whereas if I have 3 smaller reactors, I can always, affect this heat exchange better on a smaller gas volume. And when I look at the temperature versus length type of chart or type of graph, you can see in every reactor I have a small temperature increase. However, the interstage cooling drops the temperature down, immediately, and then the overall temperature versus length curve, or the average temperature versus length curve, looks like this. And intuitively, if I have more interstage cooling, the closer I get to this line. If I design my reactors in a way where I'm straddling, or the points are straddling this line in a better way, or hugging this line closely, the closer I get to ideal operating performance. Okay. For exothermic reactions, similar idea is used, and this is called multi-staging, or having multi-stage operation, but this time with a heater. So if you think about it, this is the opposite of the case we talked about before. My cold feed, it enters a furnace, so this house thing is basically a furnace. Enters a furnace, I have an endothermic reaction, I get a cold product, I heat the product in the furnace again, move it to a second reactor, cold product, heat it, third reactor, cold product. This way I want to maintain my temperature to be as high as possible, and I want to operate at the highest possible temperature. Because if you remember, we talked before at endothermic reactions, I always want to operate at the maximum allowable temperature. And this is how this allows me to do this. So if I look at the temperature versus length chart, A to B, I just push the feed to the highest possible temperature. Reaction happens, the feed drops. I heat the feed again to the highest possible temperature. Reaction happens, feed drops. I heat the feed again to the maximum possible temperature. And then the reaction happens and the temperature drops because it's endothermic. However, at the inlet of every reactor, I'm always operating at the maximum operating temperature. And again, intuitively, if I have more stages, I'm going to get closer to this line. If I can somehow control this drop so that it's not as steep, I can always get closer to this line. However, I can never operate above this line because it's the maximum allowable temperature. Okay. Let's have a look at an example before we end this lecture. So example 9.2, 9.3, 9.4, and again, your homework just involves reading these examples. Please go over them. So if I want, let's say I'm given a reaction A goes to R and then goes backwards. The optimal temperature progression, and I'm given, I'm given this reaction A goes to R, irreversible first order reaction. It's exothermic, my reaction rate is minus 75,300, and the optimal temperature, and I need to find the optimal temperature progression in the PFR. Ideally, I want to find the space-time and volume needed for 80% conversion of a feed of FA naught to the 1,000 moles per meter cubed, where CA naught is 4 moles per liter, and feed temperature is 25 Celsius. And then you're also told that your maximum allowable temperature is 95 Celsius. So how do I find the temperature progression? Again, this is an exothermic adiabatic reaction, so I want to operate along the locus of the reaction rates. So let's have a look at example or the figure 9.3, which we already developed for XA versus T. And I'm going to draw my operating line along the maximum of the reaction rates. One thing to remember about these types of charts, the chart given in your book for this example is for a CA naught is equal to 1. So this chart is valid for any type of, for this type of reaction, for any type of concentration. However, I need to correct it for the new initial concentration. This figure was prepared for CA naught equals 1, whereas we have CA naught equals 4. So you can read off the rates, but you need to multiply them by a factor of 4. Okay, so let's have a look here. So how do we read this chart? We already drew the locus of maximum reaction rates here, and this locus of maximum reaction rates is the optimum operating line for temperature progression. So because it's exothermic adiabatic, I want to operate along this line. Let's have a look and remember what type of information we're given. We're being told, find the space-time and volume for 80% conversion. Your feed enters at 25 and your maximum temperature is at 95. So let's have a look here. My feed, I'm looking at the bottom of this chart. My feed enters at 25. Maximum allowable temperature is 95. And then I want to move up from here to the locus of the maximum reaction rates, and I want to operate along this locus of maximum reaction rates until I get the desired conversion of 0.8, right? And if I draw the intersection between this desired conversion and the reaction rate I want, the reaction rate I want is minus 0.1, or this is the maximum possible reaction rate achievable at a conversion of 0.8, right? Okay. So now let's try to translate this information. So here I have a chart of XA versus T, and this I'm just extracting the line we just drew. We said we're moving from 25 to 95, moving up to the locus of our points, and then operating or moving all the way to 0.8, which is point E right here. And from the chart above, we said our reaction rate is 0.1. So since the constant, and this chart is for a CA naught of 1, since we're given a CA naught of 4, I'm going to multiply this value by 4. So my reaction rate is going to be 0.1 multiplied by 4.4. And this is basically my operating line here. We're actually from here A to B, B to C, C to D, D to E. And now in order to determine the volume, we said I'm going to extract my reaction rate data versus conversion, right? So if I look here along this line, so from A to B and B all the way to E, I'm going to extract a few points for minus RA versus conversion. So at this point, for example, I have a minus RA of 3, and the conversion of 0.1. I move up here, minus RA of between 1 and 2, let's say 1.7, conversion 0.27. I move up here, my minus RA is 0.5 and the conversion is maybe 0.525. Just read a bunch of points for reaction rate versus conversion. Then I'm going to plot 1 over minus RA versus XA. As you see here, once you have this plot, I'm going to integrate the area underneath the curve to get the volume of the reactor, right? And this is what we did here. We integrated the area under the curve to get at V over FA naught of 0.405. Once you get V over FA naught, you can always get tau over CA naught, and we're able to get the space-time for this reactor, etc. Okay. And again, you can always read off these charts to get any point you want, whether you want to get the temperature, you want to get the conversion, etc. Okay. So I'm going to stop here for the slides. Please read over these examples, and you can continue reading these slides. However, we're going to start introducing other concepts. I might go over them maybe after your test. We'll talk about it again. But for now, let's stop here, and please this week submit all your missing homework, submit all your missing Aspen tutorials if you have not done them, and just start preparing for the exam, start thinking about the exam. Exam 2 will be more difficult than exam 1, I have to tell you. So exam 1 was straightforward, it was not that complex. However, exam 2 will be difficult. So study your homeworks carefully, make sure you're prepared, come to the exam prepared. Take your time to really solve the homeworks, and please come to office hours if you have any questions, and prepare your questions for next week as well. Okay, thank you very much, and talk to you later.